day, our audience, and welcome to this morning's class. Today, we'll be looking at the variance, the moment generating function of a binomial distribution. In our previous class, we began discussing binomial distribution in terms of its probability mass function, in terms of its expected values. We equally took some questions on binomial distribution, but considering the size of the video for the class, we decided to cut it short and then begin another class that will be discussing in details the proof of the variance of a binomial distribution, and then the proof of the moment generating function of a binomial distribution, and how to arrive at the expected value and variance of a binomial distribution from its moment generating function. So that is what we have today. So we are talking about, first of all, we are looking at binomial distribution. Talking about binomial distribution. Binomial distribution. Then in this binomial distribution, we are specifically looking at variance of binomial distribution. Proof of the variance. Proof of the variance of binomial. Permit me to write BD as binomial distribution. Permit me. Binomial distribution. First of all, we are going to begin by writing the formula for the variance of any random variable, say x. The formula for the variance of any random variable, say x, is given as v of what? Of x is given as what? E of x all raised to power 2 minus E of what? X all raised to power what? 2. This is the expression for the variance of any random variable x. We now say where, as a continuation, we say where our E of x raised to power 2 is given as sum over the range of x raised to power 2, p of capital X is given as what? As x. That is the definition of E of x raised to power what? 2. Is expressed as the sum over the range of what? Of x. X raised to power 2, which is here. P of x, capital X, equals to small x. When this random variable x is, of course, a discrete random variable. And of course, you do remember that in our previous class, we did say that a binomial distribution or a binomial random variable is a discrete random variable because of the nature of its possible outcomes, being discrete, number one, and equally being finite as well. Now, and equally, these are E of x, these are E of what? Of x. This one are inside this bracket is expressed as what? Sum over the range of x, p of capital X equals small x. These are the expressions of E of x raised to power 2 and E of what? Of x. And in our previous class, we already had said that our E of x is called the expected value of a random variable, otherwise called the mean of a random variable. And when we proved this thing in our last class, which of course we refer you to, or a situation whereby you still have a problem on how to arrive at the expected value of a binomial distribution, we recommend that you revisit our class on a YouTube tagged binomial distribution. You definitely see how easy we actually made the finding of the expected value of a binomial distribution in that class. And then in that class, we concluded that our E of X is given as what? NP. If you go to that class, you are going to confirm it. So by implication, now what we are left now to show in this class is what is the equivalence of this. So at the moment we can arrive at what this is now, we come back here now and be able now to evaluate this expression in order to arrive at the variance. Okay? So of course we now say therefore, or even before therefore, we say recall that for binomial distribution, recall that P of a capital X equals small x is given as we have n combination x, P of what? Of x, Q of n minus what? X, such that x takes a value 0, 1 down to what? To n. This is the probability mass function of a binomial distribution. It was stated in our previous class. So coming over here now and replacing this P of capital X equals to small x, we are no longer talking about what? E of x raised to power 2 of any random variable x. Instead, we are talking about what? E of x raised to power 2 of a random variable x that follows a binomial distribution. And in that case, what I'm going to have here becomes what? Therefore, my E of x raised to power what? 2, where this x follows a binomial distribution, is given as sum. The range of this x begins from 0 and ends at n. So it begins from what? X is ranging from 0 to what? To n. Of x raised to power 2, this x raised to power 2 here. Then I will have, instead of writing the whole of this, I will now write this. I will now write this thing. So what I have becomes what? N combination what? X. P of what? Of x. Q of n minus what? X. This is what I'm going to write there. Okay? So another effort I'm going to make here now will be, what I have here is what? Is x raised to power 2. Then I will show us something to know whether this x raised to power 2 and that thing are equal. When someone has x raised to power 2, x raised to power 2, and that person has what? X into what? X minus 1, then plus what? Plus x. Let us confirm whether this quantity and this quantity are the same thing. If they are the same thing, it implies that they can be used interchangeably. What I have here is x raised to power 2. If you come here and say x times x now, you have x raised to power 2. X times minus x will give you minus x. Plus this x here will now cancel that what? Minus x now. So you are left with x raised to power 2. What have I just said? What I have just said is this. I have x raised to power 2. I want to know whether x raised to power 2 and this quantity are equal. I say x raised to power, x times x will give you what? X raised to power 2. The sign here is what? Minus. X times 1 will give you what? X. And I have this plus what? X. This minus x plus x will cancel each other. And I'm left with x raised to power what? 2. So this quantity and this quantity are equal. And because they are equal, I can use this quantity in place of this. And if that is an agreement by you, I will now come back here and say, therefore, this is equals. I have sum as x tends range from what? 0 to what n. Instead of writing this x raised to power 2, what I'm going to write becomes what? I have what? I open a bracket this way. I have x into what? Into x minus 1. Close it. Plus what? X. Close this bracket now. And I'll write what? N combination what? X. P of x. Q of n minus what? X. This is what I'm going to write. And if that is an agreement, of course, now I am going to use this quantity to open a bracket. Using this quantity to open a bracket means this will times this, and this will times this. And by that, what I'm going to have becomes what? I have sum as x ranging from 0 to what? To n. Then what I have here becomes what? X into what? X minus 1. Here becomes what? N combination what? X. P of x. Q of n minus what? X. This quantity will equally time this, but the sign here is plus. So I have what? Plus. When I time this, I will equally have what we call sum, because this sum is coming inside equally. X is ranging from 0 to what? To n. Of this x, then of what? N combination what? X. P of x. Q of n minus what? X. That's what we are going to have. Now, do remember that in our previous class, we showed that this quantity here is what we call the expected value of a random variable x. Just like I had earlier explained here, that this e of x is called the expected value of any random variable, what? X, which is expressed as sum over the range of x of this x. P of capital X is equals to what? X. Where is my P of capital X equals to X is the PMF of that random variable X. But this time around, we are saying that this random variable X is following a binomial distribution. And because it's following a binomial distribution now, definitely this P of capital X now, this small x now will be expressed as this. Because this is the PMF now of a binomial distribution. And if you watch, here is over the range of x over the range of x. This is what x, this is what x. P of capital X being small x is already that of what? A binomial distribution now, which is what I have replaced what here. So the entire of this quantity now is what we call the expected value of a random variable. And by implication, I can write this quantity now to be, this thing can now be written as. So permit me please to clean. Of course, remember where we began. We began by talking about proof of the variance of a binomial distribution. We began by giving the formula for the variance of any random variable x. This is how it is expressed. Any random variable x. And then, of course, this our e of x raised to power 2 is expressed as this. And our e of x is expressed like this for any random variable x. However, we are discussing of a binomial distribution. And P of capital X equals small x, which of course is called the probability mass function of a binomial distribution now, is defined as this. Within this range from 0 to what? To n. And we are saying that here it is for any random variable x. But here we are now talking about a random variable x that follows a binomial distribution. So we now have this as a sum over the range of x. We have come to realize that the range of a binomial distribution begins from 0 to n. So we become specific. X beginning from 0 to what? To n. This x raised to power 2, this x raised to power 2. It's no longer any random variable x. It's a random variable x that follows a binomial distribution. Then we replace it with the PMF for a binomial distribution. Okay? So on trying to expand this in further, we now said, let us, here is x raised to power 2, here is x raised to power 2. We're now trying to find out what is it that is equivalent to x raised to power 2. We now say x into x minus 1 plus x is the same thing as x raised to power 2, which is of course what we showed here. When we open this bracket and cancel the like terms now, we arrive at x raised to power 2. So by implication now, I can use this expression in place of x raised to power 2. And that was why I brought it in here. When I brought it in here now, of course I know that I can use this expression outside this bracket now to open the bracket. And by so doing now, then I will now say this quantity here now, multiply this x into x minus 1 will give me x into x minus 1 multiplied by that quantity. And of course, this sum equally will come in, and I have this sum here. The sign I have here is plus. Look at the plus here now. When I use this quantity now to multiply this x here, that will now give me x, n combination x, p of x, q of n minus x. This sum, of course, will equally come in, and I have it here. And I had explained that in our previous class, we made mention that the expression like this now is expected value of a binomial distribution, which we earlier had proven in that class, and then we arrived at the value is what? NP. So you permit me to clean the top of here now so we can continue this proof now. So by implication now, what we have now becomes now, what I have now becomes what? What we call sum x is running from 0 to what? To n of x into what? X minus 1 of n combination x, p of what? Of x, q of n minus what? X plus. The whole of this thing I have here is what we call NP. We call it what? NP, which is the expected value of a binomial distribution. We already had proved this thing in our previous class. You can actually try to look it up there and see what we did there. Now, we now return back here now. My interest here is how will I remove x into x minus 1 from this expression? I want to eliminate it there. And to eliminate it, this thing there, what I'm now going to do becomes now, I will say that this thing becomes what? Sum as x runs from 0 to what? To n of x into x minus 1 close it. This my n combination x can be written as multiplied by, I have n into what? N minus 1 into what? N minus what? 2 close it, all factorial, all over. Here is my x. So I have x into x minus 1 into what? X minus what? 2 all factorial. So here becomes what? Open the bracket, n minus what? 2 or n minus what? X all factorial. Then I have this thing now to be p of what? X, q of n minus what? X plus what? N. Now the question is, how did I arrive at this quantity? I arrived at this quantity by this, that this my n combination x is always written as what? N factorial all over what? X factorial into n minus what? X all factorial. That is how n combination x can be written. And because of that, this my n factorial can be written as what? N into n minus 1 into n minus what? 2 all factorial. And that's of course what I have at the numerator. And this my x factorial can equally be written as x into x minus 1 into x minus what? 2 all factorial. And that's what I have here. This my n minus 1, n minus x factorial, look at it here, n minus x factorial. So I didn't change anything from that expression that is there, okay? So I clean this one. So we move on. Now at this point in time, I have x here and I have x here. So this is my NP. So this x will cancel this x. I have x minus 1, I have x minus this will cancel this. So what I have becomes what we call sum x is running from 0 to what? To n. What I have here becomes what? N into n minus 1 into n minus what? 2 or factorial all over. What I have here becomes what? What I have here becomes x minus what? 2 or factorial into n minus what? X all factorial. Then what I have here, you see what I have here now? What I have here is p raised to power what? X. So I'm trying to show you now how can this p raised to power x now be expressed. Now if somebody has p raised to power what? X, and that person have something like p raised to power what? 2 multiplied by p raised to power x minus what? 2. Are they the same thing? The answer is yes. Because this p and p are of the same base. So I'll take one of the p and I'll sum the power. What I have here is what? 2 plus. Here is what? X minus 2. These 2 will cancel these 2. What I have here will be left with what? P raised to power what? X. So by implication, anywhere I see p raised to power x, I am free to use p raised to power 2 multiplied by p raised to power x minus what? 2. I am doing this thing because of this x minus 2 which I have here. So which means in place of this p raised to power x, what I'm going to write that place becomes what? P raised to power what? 2 multiplied by what? P raised to power what? X minus what? 2. Before I now write what? Q raised to power what? N minus what? X plus NP. I'll write it that way. So I move on small. Moving on small here now, I want to, from this particular place, I want to bring out everything that doesn't contain x and everything that doesn't contain factorial. If you watch, I have n into n minus 1. It doesn't contain factorial. I can bring it out. And I have p raised to power 2. It doesn't contain that, so I can bring it out. So if I bring it out now, what I have here becomes what? N into n minus 1 of p raised to power what? 2. Then I have sum that x is running from 0 to what? To n. What I have here becomes what? N minus what? 2 all factorial, because this one has gone outside. Then I have all over. Here is my what? My x minus what? 2 all factorial. Here is my n minus x all factorial. Here becomes, this one has gone outside, so it is p raised to power x minus what? 2 q raised to power n minus what? X plus what? NP. That's what I now have this time around. So I will now clean here. Okay? So I can make some definition. Definition I'm going to make, I can say let, okay, permit me to clean here. I will now say let t equals x minus 2. I have x minus 2. I'm saying let t be equals x minus 2. And if this t equals x minus 2, it implies that t plus 2 equals x by bringing this minus 2 over there. I equally say let s equals, here is n minus 2 equals what? N minus what? 2. So if these definitions are true, I will now say therefore, what I have becomes what? N into what? N minus 1 p raised to power 2. We now have what? Sum. Here was x, and I have realized that x is the same thing as t plus 2. So I will now write what? T plus what? 2, ranging from 0. Here is my n to my what? To my n. So we move on. Then here is my n minus 2, and my n minus 2 is already s. So I will now write here to be what? S factorial all over. Here is my x minus 2, and my x minus 2 is t. So I will now write t factorial, open a bracket. Here is my n. So I will have my what? My n. Here is my n. The sign here is what? Minus. My x is t plus 2. So I have what? I open another bracket, t plus what? 2. Cover it and cover the bracket well. So I will now come here. So here becomes what? P raised to what? X minus 2 is given as what? T. So I have this is to be t multiplied by. Here is my q of n minus, open a bracket, t plus what? 2. Cover the bracket. Plus np. Sorry, the proof is becoming a little bit lengthy, but I know you are going to enjoy it. Okay? So this thing becomes what we call n into n minus 1 p raised to power what? 2 sum t plus what? 2 equals 0 to what? To n. Here becomes what? S factorial all over what? T factorial into. Here is the same thing as saying n minus 2. This is n. When this thing comes over here, it becomes minus. We now have what? Minus what? T. Close it. This is all factorial. This is all factorial. Here becomes what? P raised to power what? T. Q raised to power what? N minus what? 2 minus what? T. Then we have what? Plus what? NP. You may have not had any challenge from the beginning of this as we are going. So this is where, of course, we said that what we had earlier was expressed to be this. Our interest was to remove this thing, And that was what led us to expand this thing to arrive at this, for us to cancel this, and we began to come down to this point. So you permit me to clean the top while we conclude the proof up here. We are making plans to buy or to procure very large board, such that this kind of proof will be continued till the end without killing anything in case of confusing our audience. So what we have is here. So we now say this is what n into n minus 1 of p raised to power what 2, which is what we have here. Then we now have some that are t plus what 2 ranging from 0 to what to n. Here becomes our s factorial all over. Here is our t factorial. We open a bracket. Here is n minus 2, and n minus 2 is s. So in place of this n minus 2, I am free to write s minus. Here is my t, so I have my t, close it, all factorial. Here is what? P raised to power what? T, then q raised to power. Here is my n minus 2, and my n minus 2 is s, so I have s minus what? T plus what? Np. Sure. Now, there's something I would want us to know. Here, we were told earlier that the range of a binomial distribution begins from 0. And if you bring these 2 over here, what you are going to have is what? Is minus 2. So if you have minus 2 there, it means you must add a 2 here for you to remove that minus. And the moment you add anything here, you are bound to subtract it from here. Otherwise, you are now introducing something into the range that is more than the initial range. So here, if you bring this thing over here, it will be, because 2 and 0 are like terms. So if this 2 comes over here, it becomes minus. So our interest is to make sure that it begins from 0. So we must add 2 here. And if we add 2 here, you must remove that 2 there. So you have n into n minus 1 of p raised to power 2, sum that t is now beginning from what? 0. Here becomes n minus what? 2 of what? S factorial into t factorial into s minus what? T, then factorial p raised to power t, q raised to power s minus what? T plus what? Np. And we know that this our n minus 2 is given as s. So the same thing is, it is the same thing as n into n minus 1 p raised to power 2 sum of t running from 0 to what? To s of what? S factorial into t factorial into s minus t or factorial p raised to power t q raised to power s minus what? T plus np. Now, we already had said earlier that the whole of this quantity that is here is the sum of the PMF of a random variable over the range. And once you sum the PMF of a binomial distribution over its entire range, the answer is what? Is 1. So the entire quantity here now is the same thing as 1. And in that case now, what you are now going to have becomes, you have that this thing becomes what? N into n minus 1 of p raised to power 2. The whole of this thing is 1 multiplied by 1 plus this what? Np. And in that case, what you now have becomes what? N into n minus 1 p raised to power 2 plus what? Np. This is what you are going to have as that of e of x raised to power 2. Then we now conclusively conclude the variance. Okay? But remember, we say recall that our var of x is given as what? E of x raised to power 2 minus e of x all raised to power 2. But we have gotten that this one is all of this. So we now say, therefore, in place of this, we have what? N into n minus 1, then p raised to power 2 plus what? Np. The sign here is what? Minus. We showed that in our previous class, we already had proven this thing, and the answer is Np. So we have what? N what? P all raised to power what? 2. So we now try to open the bracket here now. Open a bracket here now. Let us first of all use n to open. If you use n to open, what we are going to have, n times n will give us n raised to power 2. N times minus 1 will give us minus what? N. This way, p raised to power what? 2 plus what? N what? P minus n what? N squared p squared. Now, when we now use this p squared to open a bracket, what we are going to have is what? N squared p squared minus this our n p what squared plus n what p minus n squared p squared. Now we are seeing n squared p squared minus n squared p squared. So this and this can go. And if this and this can go, what we are left with is what we call, here is our n what? P. This is our np that is here. The sign here is minus. We have minus what? Np squared. So we now try to see what is it that we can factor out here together. Np is here and np is here. So we have what we call np, open the bracket. What will be left here is 1 minus what? P. We close it. And we remember that 1 minus p is q. Because we know that we said that p plus q is equals 1. So therefore, we have that if you keep this q here, q is equals, here is 1 minus what? P. So this 1 minus p is the same thing to the q. So this thing implies that what I have is here npq. And npq, of course, is the variance of a random variable that follows a binomial distribution. So we have conclusively proven the variance of a binomial distribution. And as a way of recap, do remember that we earlier had said that the expected value E of x for binomial distribution is given as what? NP. And then var, which we have now proven now, is given as what? NPQ. So when they can equally ask you that a binomial trial where the trial is repeated up to 8 times, its expected value is something like what? 5. What is the probability of what? Of success. So it's the question of you making this thing subject of formula. Making P subject of what? Of formula. Or they will now tell you that if the variance is given as this, and the probability of what? Of success and then failure is given as that, how many trials are involved in that binomial distribution? You'll be able to make this n subject of formula in that case. Okay? So, by implication, the moment you know the probability of success and you know the number of trials involved in the binomial distribution, you'll be able to get the expected value by saying the number of trials multiplied by the probability of what? Of success. For us now to get that of what? Of variance, it is still simple. You know the number of trials, you know the probability of what? Of success, you know the probability of what? Of failure. The moment you multiply it up now, you will not have any problem. So it becomes the number of trials multiplied by the probability of success multiplied by the probability of what? Of failure will be able to give you that of the variance of a binomial distribution. Okay? If you watch, we were so detailed in the proof of the binomial, the variance of a binomial distribution, and continuing to prove the moment generating function in this size of the video we already have. Then we are now going to make it to be boring to our students. So we are quickly going to cut this video here and then take up another class that is going to talk about the moment generating function of a binomial distribution and how to arrive at the expected value NP and then the variance NPQ of a binomial distribution from its own moment generating function. Thank you very much. Don't forget to subscribe to our YouTube videos if you like our classes. Thank you very much.